Okay, reviewing back from the previous session. So from the homogeneous equation of the second order circuit, yeah, we can derive three possibilities of solution. So after putting into after forming the characteristic equation from the normalized form of the second order equation. So normalized here means that the coefficient in the second derivative term should be made into one. Okay, so whatever after you derive the equation using Kirchhoff current law, Kirchhoff voltage law, Ohm's law, capacitance law, and inductance law, you have to make then the coefficient of the second order term to be one. And from there, then you have the normalized form d square x dt square t plus 2 zeta omega n dx dt plus omega n square xt. Then you can rewrite it as characteristic equation s square plus 2 zeta omega ns plus omega n square equals to 0. So from here, then we have derived, yeah, we have obtained the characteristic equation, and that should be 0, yeah, assuming that xt, the solution of xt is k times exponent xt, k the coefficient times exponent st. So the first derivative will be sk exponent e st. The second derivative is s square k exponent st. So putting it back into the equation, the normalized form equation, we will obtain this equation, and this equation should be 0 because this is homogeneous equation, and this cannot be 0. So it means then the characteristic equation, this one, that has to be 0. By putting making it into root equation from like this, we obtain s to be minus the root, yeah, of this characteristic equation to be minus zeta omega n plus minus omega n times zeta square minus 1, from which we will obtain three possibilities of the value of zeta, yeah, the damping coefficient, the damping constant. If zeta is larger than 1, it means we will have two distinct roots where both are real number. Where it is the case is called as overdamp case. Yeah, like this, xt then equals to k1 exponent s1t plus k2 exponent s2t. Case 2 is if zeta is less than 1, which means that the value under this square root will be a complex number, yeah, a complex number. So the whole s root will be we will obtain two complex conjugate roots. Yeah, if xt is expressed as k1 exponent s1t plus k2 exponent s2t, then the first the s equals to minus zeta omega n plus minus j omega n square root of zeta square minus 1, or 1 minus zeta square. And the term omega n times square root of 1 minus zeta square is renamed as omega d, yeah, the damping frequency, the damped oscillation frequency. This is the frequency inside the damping curve. Okay. If xt is real, okay, so it means from this equation k2 should be the complex conjugate of k1. Sigma is the damping factor, so xt here will be equals to exponent minus sigma t times a1 cosine omega dt plus a2 sine omega dt. Yeah, this is obtained from that exponent st equals exponent minus zeta omega n plus minus zeta omega d times t, and this is equals to exponent minus zeta omega nt. Okay, and this becomes sigma zeta omega n the sigma part, and exponent minus plus zeta omega dt. Okay. Exponent minus plus zeta omega dt, from Euler's law, we know that this equals to cosine omega d t minus plus j sine omega dt. Okay, so from here, then we obtain this general solution, yeah, of xt equals to exponent minus sigma t, yeah, from zeta omega n. Zeta omega n is sigma t plus multiply by a1 cosine omega dt plus a2 sine omega dt, where k here equals to a1, assuming that k1 equals to a1 plus j a2 divided by 2, and since k2 is the complex conjugate of k1, yeah, and s equals to minus sigma plus minus j omega dt, so means here k2 equals to a1 minus j a2 over 2. Okay, so xt here equals to 2 of the real term of k1 exponent minus k1 exponent st, right? K1 exponent st, or exponent minus sigma j omega dt. In case 3, zeta equals to 1, yeah, which means that this term equal to 0. So we only have equal root, one single root, which is real number. Yeah, and that root is equals to minus zeta omega n. The solution, the general solution of xt will become x1, xt equals to b1 plus b2 t exponent st, which is exponent minus zeta omega n t. T exponent st is a solution if only if the characteristic equation here equals to 0 and 2s plus 2 zeta omega n equals 0, which this means that zeta equals to 1. Yeah, zeta equals to 1, or s equals to here minus zeta omega n. If this is 2s plus 2 zeta omega n equals to 0, mean 2 s equals to minus zeta omega n, this one, or zeta equals to 1. Yeah, this term equals to 0. Okay, so then t exponent st becomes the solution. Okay, let's try to do some example. Yeah? Try to see some examples. For example, here we have, this is the equation for dx square, d square x dt square plus x 8 dx dt plus 16 xt. If we make this into normalized form, we have to divide each term with 4. So this becomes d square x dt square. Sorry, this is different, yeah, not the same. Let's say this one first. Yeah, this is already in the normalized form. D square x dt square t plus 4 dx dt plus 4 xt equals to 0. So the characteristic equation becomes s squared plus 4s plus 4 equals to 0. Yeah. So from here, after we make root, yeah, of this equation. So remember that this equals to 2 zeta omega n, and this equals to omega n squared, right? Omega n squared equals to 4, so omega n equals to 2. 2 zeta omega n equals to 4, and omega n here equals to 2, to zeta equals to 1, right? And so here what we obtain. Then taking root of this equation, s squared plus 4s plus 4 equals to 0, can be expressed as s plus 2 squared. So s equals to minus 2, right? So we have only one single root, or we have two roots, but they are equal, which is minus 2. Yeah, so this is case number 3, right? The overdamped case. Critically damped case. Zeta equals to 1. Zeta equals to 1. So from here, xt equals to b1 plus b2t exponent st. Yeah, and xt, since s will be equals to minus 2, x here equals to minus 2 from here, minus 2. Yeah. Zeta equals 1, this is critically damped case. Xt equals b1 plus b2t exponent minus 2t. Second example, for d squared x dt squared, t plus 8 dx dt plus 16xt equals to 0. So we have to normalize this equation. We divide each term with 4, so that we will obtain the coefficient of the second derivative to be 1. So d squared x dt squared plus 2 dx dt plus 4 xt equals to 0. So this is 2 zeta omega n. This is z omega n square. Omega n square equals to 4. Omega n equals to 2. 2 zeta omega n equals to 2. So omega n, this like this. Zeta omega n is 2. So zeta is 1 over 2 or half. Okay. Writing down the characteristic equation, s squared plus 2s plus 4, yeah, equals to 0. And this can be simplified into s plus 1 square, yeah, 2s, this plus 3 equals 0. So s plus 1 square equals to minus 3. Okay. So s plus 1 equals to the j square root of 3, right? Because my square root of 3 is an imaginary number. So s equals to minus 1 plus minus j square root of 3. So here we have zeta is half, zeta is less than 1. So this is an underdamped case. Okay, an underdamped case. So the roots are complex conjugate. We have 2 roots with plus minus conjugate, yeah, minus 1 plus minus j square root 3. It's an underdamped case. The solution will be cosine and sine. The sigma is omega n zeta omega n. Yeah, zeta omega n is 1 here. Omega d is omega n times square root of 1 minus zeta squared. And zeta is half here. So 1 minus half square is a quarter, or 0.375. So this equals to square root of 3. Okay, here. So this becomes the damping, the damp oscillation frequency. The damp oscillation frequency. So then the solution will be xt times exponent minus sigma t times a1 cosine omega dt plus a2 sine omega dt. Exponent sigma is 1, exponent minus t plus a1 cosine omega d we put from here. Cosine square root of 3t plus a2 sine square root of 3t. So now we need to find a1 and a2, yeah, from here. This will usually be given if the some boundary conditions are given also in the circuit. Okay, so we have the first circuit is a parallel circuit with connected to a current source IST. RLC parallel circuit with resistor equals to 1 ohm, inductance is 2 Henry, capacitance is 2 Farad. Solve the circuit, yeah, the voltage. So we write the homogeneous equation first. Yeah, this is the case when IST equals to 0. So this becomes C d square V dt square plus 1 over R dv dt plus V over L equals to 0. So we insert the number for C, R, and L, 2d square V dt square plus dV dt. R is 1 ohm plus V over 2 equals 0. We divide by 2 to normalize the second order differential equation to become d square V dt square plus 1 over 2 dV dt plus 1 over 4 V, okay, equals 0. So from here, we obtain this one, 1 over 4 is the coefficient for the zeroth order term, half is the term for the first order term. Yeah. So the characteristic equation is S squared plus S plus 2 plus 1 over 4 or quarter equals to 0. Putting it into root, we obtain S equals to minus 1 quarter, yeah, 1 quarter, plus minus J square root of 3 over 16, right? The omega n here is the square root of 1 over 4, so this is half. And half here equals to 2 zeta omega n. So it means zeta omega n equals to 1 over 4. Omega n we put here half, so zeta equals to 2 over 4 or half. Okay. The sigma then equals to zeta omega n. Yeah, the damping, the damp coefficient is zeta omega n or 1 over 4. So omega d equals to omega n times square root of 1 minus zeta square. Okay, or this one, yeah, half times square root of 1 minus half square. The value is square root of 3 over 4. So the solution is in cosine and sine, yeah, because this is under damped case, yeah, case number 2. VCT equals to exponent minus T over 4. This is the sigma. This one is the sigma. Then the D, omega D is this one. A1 cosine square root of 3 over 4t plus A2 sine square root of 3 over 4t. The second problem is series circuit with voltage source Vs connected to resistor, capacitance, and inductance. The values are given. Resistor is 2 ohm, inductance is 1 Henry, the capacitance is varied, yeah, 0.5 farad, 1 farad, and 2 farad. Classify the responses for the given values of C. So the general form of the equation for the homogeneous equation, yeah, when voltage source equals to 0 is L di d square I dt square plus RR di dt plus I over C equals to 0. So we have to normalize this. So we have to divide by L. It become d square I dt square plus R over L di dt plus I over LC. Okay, since L is 1 Henry, that's why this becomes 2 ohm here, the coefficient for the first order term, and this become 1 over C, or the coefficient of the zeroth order of the equation. Yeah. So then omega n is in these terms. Yeah. Omega n comes from the zeroth order, so 1 over C equal to omega n square. So omega n equals to 1 over square root of C. Then 2 zeta omega n equals to 2. So zeta then equals to 1 over omega n, or square root of C. Yeah. So from this case, if the capacitance is 0.5 farad, so the square root of 0.5 is less than 1. So we will have under damped case, the second case. If the C equals to 1 farad, then we have zeta equal to 1, in which we have critically damped case, yeah, or case number number 2, number 1. And then when C equals to 2 farad, we will have overdamp case. Yeah, when the C equals to square root of 2. Square root of 2 is larger than 1. So we have overdamp case. Here the discriminant is 4 minus 4 over C. This is obtained from the linear equation solution. So we are just, the question is just to classify the responses. We just classify whether it is underdamped, critically damped, or overdamped, depending on the values of the capacitors. Okay, so in the previous slide, we have been able to write the general solution, of the circuit, but then the constants are still there. So, for example, if it is underdamped, we have exponent minus sigma t times a1, cosine exponent omega dt plus a2 sine a1 cosine omega dt plus a2 sine omega dt. There is a1 and a2 there. If it is critically damped, then we have b1 plus b2t exponent st, right? If it is overdamped, this one, we have k1 exponent st plus k2 exponent s2t, right? K1 exponent s1t plus k2 exponent s2t. How to determine now the k1, this coefficient, k1, k2, a1, a2, b1, b2, okay? So first is, of course, we have to re-express the second order equation into normalized form. D square x dt square t plus 2 zeta omega n dx t plus omega n square xt equals to a. Okay, the general solution of this will be like this. Yeah, remember that this is the homogeneous solution. Yeah, this part. Oops. Wait. No. Okay, one moment. Yes. Share screen. Okay. Yeah. Okay. Yeah. So this comes from the homogeneous solution. Yeah. C homogeneous. Yeah. CH. This comes from the particular solution, right? Remember A. If this is A2 previously, this is A2 and this is A1, right? So the particular solution is obtained where S xt equals to particular solution A over A2. Yeah, because then the constant, yeah, when the forcing function is a constant A, then the particular solution is constant also, A divided by A2. The derivative, the first derivative here will be 0, second derivative also will be 0. Okay, so A2 xt equals to A, xt equals to A over A2. So since we know xt, the general solution is equals to the particular solution plus the homogeneous solution. So this comes from the homogeneous solution. This is from this particular solution. Okay, remember? The homogeneous solution as we have derived in the previous two slides, yeah, we have three cases: over dam, critical dam, and under dam. Then, okay. So x at 0 plus, the initial condition will be minus a divided by omega n squared will be equals to k1, k2, because at x0, the value of exponent s1t will be equal to 1, right? The value of this will also be equal to 1. So x at 0, the initial condition, minus a divided by omega n squared equals to k1 plus k2. The derivative, the initial condition for the first term derivative equals to, the derivative of this is 0. So this equals to s1 k1 exponent s1t. Since it is at 0, the value will be 1. So will be equal to s1 k1 plus s2 k2. Okay. Okay, I have to erase this also. So this is the solution when the zeta is the root is, we have two roots, yeah, two positive roots, and they are not equal. So this is when zeta is larger than 1, the overdam case. In the overdam case. So when zeta is less than 1, then we have underdam case, yeah, underdam case, and the solution is exponent minus sigma, exponent sigma minus sigma t, right? Or minus zeta omega nt times, this is the homogeneous solution, times a1 cosine omega dt plus a2 sine omega dt. The particular solution is still this one, a divided by a2, or a divided by omega n squared. So the initial condition will be t equals to 0, right? Cosine 0 equals to 1. Sine 0 equals to 0. Exponent 0 is 1. So we have then x at 0, initial condition, equals to a divided by omega n squared plus a1. Or a1 equals to initial condition of x at t equals to 0 minus a divided by omega n squared. The derivative, yeah, the initial condition for the derivative, the first derivative is, the derivative of this is 0. Derivative of this will be minus sine omega dt, okay, which means it is equals to 0 as well. Derivative of this is cosine. Cosine 0 equals to 1, so we have a2 dt, yeah, a2 omega d, and this is equal to minus z omega n times a1 equals to the first derivative, initial condition of the first derivative. Then for the third case of critically damped, yeah, when zeta equals to 1, xt is a divided by omega n squared plus b1 plus b2t times exponent minus z omega n t. So then the initial condition minus a over omega n squared at t equals to 0, this will be equals to 1. This will be equals to 0, right? Because so xt minus a divided by omega n squared equals to b1. To obtain b2, we have to use the initial condition of the first derivative. Yeah, in which case we will obtain minus zeta omega n b1 plus b2, yeah, plus b2. Okay, let's give some example. We have this circuit RLC, parallel. Yeah, we have the initial condition of the voltage at the C is VC 0. Resistor value is given to ohm, inductance is 5 Henry, capacitance is 1/5 farad. Initial condition of current flowing through L minus 1 ampere. The voltage at 0, voltage at the capacitance at 0 is at t equals to 0 is 4 volt. Yeah, now solve this particular circuit. So using KCL, we obtain IR plus IL plus IC equals to 0. Then we use Ohm's law, inductance law, and capacitance law, V over R plus 1L integral ID Vx dx from 0 to t plus C dvc dt equals to 0. We make derivation again, so dvr dt dv dt times 1 over R plus 1 over LV plus C d square V dt square. Then we normalize it, so the second term, so the coefficient of the second order, which is the with C there, becomes 1. Yeah, so d square V dt square. So it means we have to divide by C, right? D square V dt square plus this become 1 over RC dv dt, right? This become 1 over LC V, yeah, equals to 0. So from here, this is the, so this will be equal to omega n square, right? This 1 over LC equal to omega n square. 1 over RC will be equal to 2 zeta omega n. The characteristic equation we have after inserting the value of R, L, and C. So S square plus R is 2 ohm, C is 1 over 5, so 2.5 S. And LC here is 1, 0. So from here we obtain omega n equal to 1. 1. Then zeta 2 zeta omega n equals 2.5. Omega n equals 1. So 2 zeta equals to 2.5. Zeta equals to 2.5 divided by 2. So let's see. We have to write, yeah. So this equals to 2 zeta omega n. So this equals to omega n square. So omega n we obtain to 1. 2 zeta 1 equals to 2.5. Zeta equals to 2.5 divided by 2. Yeah? So it's supposed to be 1.25. Yeah? I'm not sure why is this 1.5. Okay, wait. Here is again. Then S, based on this characteristic equation, we can calculate using the root equation for quadratic equation. Yeah, S will be equals to minus 2.5 plus minus square root of 2.5 square minus 4 times 1 times 1. Yeah, so divided with 2 times 1 here, the coefficient of S square. So we obtain minus 2.5 plus minus 1.5 over 2. Yeah, zeta is larger than 1, so we have overdone case. So the root is minus 2.5 plus 1.5, which is equals to 4. Yeah, 4 divided by 2 is 2 here, the first root. The second root is minus 2.5 minus 1.5, or equals to minus 1 over 2, so minus half. So this is the general equation, the homogeneous solution. Okay. So to determine the constants, we need voltage. Since we are solving the voltage here, we need the voltage at 0 plus and the derivative of the voltage at 0 plus. So voltage at 0 plus here will be equal to this Vc 0, equals to 4 volt. Okay. Then using KCL at t equals to 0 plus, so Vc divided by R equals to IL 0 plus C dv dt equals to 0. So now we want to find dv dt at 0 plus. Okay, this is 4 divided by 2 ohm. Okay, here. So dV dt here then divided by C. C is 1/5. Minus is IL is known, minus 1 ampere, divided by C also 1/5. Yeah, because we want to find dV dt at 0 plus. So from here we obtain dV dt, initial condition of the first derivative of the voltage equals to minus 5. Okay, since this is case 1, yeah, for overdamp, yeah, remember for overdamp from the previous slide, this is the solution. Yeah, we can calculate then K1, K2 from this and from here also. K1, K2 equals to 4. Yeah, then minus 2 K1 minus 0.5 K2 equals to minus 5 from here. Yeah, dV dt. Then using this, we can obtain K1 equals to 2, K2 equals to 2. So the general equation for this circuit will be Vt, the voltage T equals to 2 times exponent minus 2t plus 2 times exponent minus 0.5t. Now this is simple since there is no term on the right hand side of the equation of this of the characteristic equation. Yeah, so there is no particular solution, no xt t. There is only homogeneous solution. Okay, so this is the steps in solving this equation. Yeah. First is deriving the model from electric circuit laws, Ohm's law, KVL, KCL, capacitance law, inductance law. Step 2 is using mathematics to find from the characteristic equation to find the omega n and to find the zeta. Then step 3 is finding the roots so that we know the S. Yeah. Then forming the solution, finding the constants by using the initial values that are given in the problem. Okay. If not given, the V0 plus and dV0 plus, you find the VC here from the VC 0 here. And you find the dV dt at 0 plus from the IL 0 here. Okay, using KCL, Kirchhoff current law also. Okay. Then we can visualize the response using Octave or MATLAB. Yeah, Vt equals to 2 exponent minus 2t plus 2 exponent minus 0.5t. So this is from 0 to 20 seconds with 1000 points in between. So plotting here, dV as magenta with color magenta, and the point is plotted as circle. Okay. So this is the response of overdamp parallel RLC circuit. Zeta is larger than 1. The case number 1. Case number 1 overdamp. Another example, we have resistor series RLC, series with resistor 6 ohm, inductance 1 Henry, capacitance 0.04 farad. Initial condition of the current at the inductance is given 4 ampere. The initial voltage of the capacitor at t equals to 0 is also given, minus 4 volt. So let's derive the model here. We say KVL, right? VL plus VC equals to 0. Then changing the VR, VL, and VC using the Ohm's law, inductance law, and capacitance law. RIT plus L didt plus 1 over C integral IX dx plus the initial condition here at the capacitance equals to 0. deriving towards time. So this becomes di square. So from here it becomes di square dt. This becomes di dt. This becomes I dt. This becomes 0, equals to 0. So the second order term is this di square dt with L. So we divide with L, so that to make the equation to be normalized. Okay, so becomes di square dt square. This becomes r over L di dt. This becomes 1 over LC it equals to 0. So we insert then the value of R, L, and C. So we obtain this. Then we rewrite it as characteristic equation. S squared plus 6s plus 25 equals to 0. From here, we obtain omega n squared to be 25. Omega n equals to 5. 2 zeta omega n equals to 6. Yeah, so zeta omega n equals to 3. Zeta equals to 3 divided by 5, or 0.6. The roots from here, we use the equations minus b plus minus square root of b minus 4a divided by 2a, right? So we obtain minus the root to be s1, s2 will be equals to minus 3 plus minus j4 respectively. Okay? Since this is a complex root, so we know that this is under damped case. Yeah, the second case. The damped oscillating frequency become this one, J4, J omega D. And this is the damping coefficient. So the solution, the homogeneous solution form will be equals to IT equals to exponent, the damping coefficient, exponent sigma T, yeah, or minus 3T times A1 cosine 4T plus A2 sine 4T. Then we need to find A1 and A2. The current at 0 here equals to 4 ampere. Okay. Now the derivative, so it means from here, it is 4 ampere, exponent 0 is 1, sine 0 is 0. So we obtain A1 here. A1 equals to 4. Yeah. To compute the IDT at the t equals to 0, so because it is not given here, so we have to use KPL. Here again, no switching or discontinuity at t equals to 0. Use t equals to 0 or t equals to 0 from 0 plus, so means from the right. VL equals to L di dt, right? The I is given here. L di dt, yeah, using PVL, so this equal L di dt here equals to minus Ri, yeah, minus Ri minus Vc, using Kirchhoff voltage law. I at 0 is known. Vc at 0 is known here. Okay. So L from here, then we obtain the IDT equals to minus 20. Yeah, calculating from here, this is minus 4. The R is 6 ohm times 4, 24, right? Minus 24, then minus 4. Minus 24 plus 4 equals to minus 20. So this we can insert into this equation, right? The IDT equals to minus 3 IT plus exponent minus 3 minus 4, A1 is 4, minus 4 A1 sine 4T plus 4 A2 cosine 4T. This equals to minus 20 at t equals to 0. This is minus 20. Equals to minus 3 times 4 plus, this is, it becomes 1. Yeah, exponent 0 is 1. This is 0 and plus 4 A2. So from here, we can obtain the value of A2 to be equal to -2. The general equation then becomes IT equals to exponent minus dt. Okay, A1 is 4 cosine 40 minus plus A2 is minus 2 sine 40 ampere. 40 larger than 0. Then the voltage C, T, at the capacitance equals to minus RIT minus L di dt. So this then equals to the voltage at 0, yeah, plus integral 1 over C integral IH dx. So VCT equals then exponent minus 3t times minus 4 integral this one from the integral of this part plus 22 sine 4t sine volt t. Okay, if we plot then the current and the capacitor voltage, the current will be the red one. This one is the current. The current is exponent minus dt, so under them case for this one. Yeah. Then the voltage is the blue part. Voltage is here, exponent minus dt minus cosine 44, cosine 40 plus 22 sine 40. This one. Yeah. Another example. Okay. So time is up for the second session.